an electric field, the strength of the electric field is given by F over Q. But that has no meaning. When I first learned that formula, I didn't understand anything behind it. So let me give you the proper visualization that helps me understand and should help you understand as well. Hopefully, we have some audience members who turned down their music. Now let's take a look at what this visually represents. Now, first and foremost, to have an electric field at all, I need what? I need a charge, some kind of a charged particle. Now, let me get out my first marker that comes out of my back pocket, and it happens to be maroon. So here I have some electric charge, and I'll denote that with this maroon pin, right, plus Q. And of course this charge is going to create some kind of an electric field, right? And let's see what marker comes out. It's orange. So I'm going to denote the electric fields created by this maroon charge by orange. So because it's a positive charge, which way are the field lines going to go? They're going to radiate outwards, right? So it's going to look something like this. That right there are the electric field lines of any alpha particle, whether it be a proton, positron, whatever, right? So that right there is electric field for my positive test charge. Now I'm going to go ahead and put some kind of a test charge within the electric fields of this charge, right? Let's go ahead and fix the camera of our live viewers so that they can actually see what's going on. So there we go. Hopefully it's not too low. Now let's, as I said, place some kind of a charge within this electric field. I'll use the color pink. So here I have some kind of a positive test charge, and there it is. There it is in pink. Okay, and what's going to happen to this charge? Well, there's going to be a force on this charge, right? So that force is going to be proportional to however many coulombs this charge is. So, for example, if this charge were 3 coulombs versus if it were 9 coulombs, when would the electric force on this charge be greater? Well, if it has a larger amount of coulombs, if it carries a larger amount of charge, it's going to be more repelled by the electric force created by the electric field of this positive charge. Okay? So, for example, if this positive test charge were 3 times as charged, it would be 3 times more repelled. In other words, it would have 3 times more of the electric force. Okay? How do I know that? Well, if I just go ahead and multiply both sides of this equation, what I get is simply F is equal to EQ. And what that tells me right here is that the force created by the electric field of some parent charge is going to be proportional to however many coulombs my test charge is. Okay? So that's worth writing down, as a matter of fact. It's so important. Why don't I write down whoops, this one is there. No surprise, right? So the force created, the electric force exerted on, and let's call this Q3. Okay? So the electric force exerted on Q3 is going to be proportional. It's going to be proportional to however many coulombs Q3 is. Coulombs of Q3. So hopefully that makes sense. Essentially what I'm saying right now is that the electric force exerted by the electric field of some carrying charge is going to be proportional to however many coulombs my test charge is. So if my test charge is 1 coulomb, the electric force on it is simply going to be the magnitude of my electric field. Okay? So if my test charge is 2 coulombs, it's going to be the electric force exerted on it is going to be the magnitude of the electric field created by the parent charge times however many coulombs my test charge is. Okay, so hopefully that gives you a nice intuition of what an electric field is, right? So the electric field, the strength of the electric field is proportional to the electric force created by that field. Okay, now let's move on to the lesson. And in the lesson, we're going to explore this formula a bit deeper, right? We all know that the electric field is a vector field. So it has a magnitude and it has a direction. Let's talk about those two things. So let's see what marker comes out of my back pocket, and it's black. So let's go ahead and write down the magnitude. We know that the magnitude of our electric field, the magnitude of the electric field is going to be proportional to the electric force generated by said field. Okay? And what about the direction? The direction of the electric field. Well, as you can tell, this F is also a vector. This electric force is also a vector. So the electric field is going to point in the direction of the electric force. So I can just go ahead and write that down as such. The direction, dir, of the electric field, E hat, is going to equal the direction, dir, of my electric force. There it is. There it is. In its full mathematical word. The magnitude and direction of the electric field. Now let's move on to the lesson as soon as I can find the cap for my marker. Let's go ahead and resolve that. Okay, here it is. So let's go ahead and move on to the lesson. I'm aggressively erasing this board, as you can see. Now, during the lesson, I want to give you some kind of a visual perspective of all the different types of electric fields there are, because it's not just the positive or negative charges that exist out there. But first, let's begin with those two. So here I have my positively charged proton, and my proton is going to have an electric field that radiates outwards. So what does that mean? That means that my proton is going to have field lines that simply radiate upwards, much like this. So here are the field lines of the electric field of my proton. Now, you might say, why should I take your word for this? Refath, why should I believe that the electric field lines of the proton look like that? Well, simply said, let's say we have a test charge, and of course, I've lost the cap once again. Now, let's say we have a test charge somewhere near the vicinity of my proton. Okay? This test charge is going to move in a certain direction, right? Thank you for the input, viewers. Now, this electric charge is going to move in some direction, and that electric force is going to be warm. That electric force is going to be in the direction of the electric field. So let's go ahead and write that down. F, and my electric field, of course, I'll denote with this green letter E hat. So the direction of E hat, as you can see, is equal to the direction of F hat, okay? They're the same. So that's exactly how we discern the electric fields of alpha particles or positrons or protons, whatever. You just put a test charge within the vicinity of the electric field and you watch how it behaves, watch its movement, and then you track out that movement over the vicinity of the field lines, okay? So that's the field line of a proton. What about an electron? Right, is it much different? Well, let's take a look. Here I have an electron, a negatively charged particle, and what are its field lines going to look like? Well, unlike the proton, these field lines are actually going to go inwards. Okay? And I'm assuming, of course, that I have a positive test charge. Okay? So, for example, alpha particles. So the field lines of my negatively charged electron are just gonna point inwards. Something like this. Okay? As you can see, the electric field lines of my electron point or converge inwards into my electron. Okay, so these are the field lines of the proton and electron. And what if we have a dipole? In other words, what if we have something like this? Okay, well, it's too deep in my bag, otherwise I would have shown you. But what if we have a positive and a negative charge in the same field? In other words, a dipole, right? An electric dipole. So what I would have is essentially this, but now the field lines are going to kind of travel between each other. So let me show you what I mean. Instead of just discrete, separate field lines, they'll connect with each other, something like that. Right? So positive will go to negative. As you learned from your high school physics class, the positive charge will attract the negative charge, right? Opposites attract. So we'll have something like this, right? And of course the rest stays the same. Boom, from plus to minus, from plus to minus. Okay, so that's the electric fields of an electric dipole, right? It looks something like, what would you describe this as? Maybe some kind of a annulus, right? Annulus, that's what you call it. It's got kind of like a circle, but with another concentric circle carved out of its shell. Okay, so that's the electric field of a dipole. Are there any more interesting fields I should show you? Yes. What if we have a cylinder? I think they kill mosquitoes like that. They take big bags of cylinders and they put some kind of poison in it to kill mosquitoes. But instead of putting poison, we're going to put electric charges. Okay? So let's see how that's going to look like. So, we have some kind of big cylindrical wire. Okay? And on this wire, I'm going to have trillions of charges. And these charges are going to emanate, they're going to create some kind of electric field, okay? And let me just grab into my pocket. And how's that electric field going to look like? Well, it's simply going to radiate outwards of my cylinder, something like this, right? Nothing new, nothing crazy, but just to give you a sense of how different electric fields look like, okay? I might even have an infinite plane, an infinite sheet of electric charges. So something much like this. If I have some kind of plane, a planar region, and my plane only had negative electrons on it, so maybe I kind of charged up my plane negatively, so it'll have a lot of electrons on its surface. What are its field lines going to look like? Well, quite easy and simple. The field lines are going to be sucked into the plane, something much like this, So it's going to protrude inward into the plane. So something like that. And those are the field lines of a plane, a cylinder. You can even have an infinite line of charges, right? Because we can use calculus, there's no limit to what we can do. So for example, you can have some kind of infinite line of positive or negative charges, whatever you want. So let's say I have some alpha particles right here, right? And of course it's going to look much like the cylinder because these are alpha particles. They'll have electric field lines protruding outwards of my infinite line. Okay, hopefully that gave you an idea of the many types of electrical field lines that can exist, right? Okay, so now what I want to do is give you a brief idea of notation, of visual notation. And let's go ahead and erase all of this. Of course, I'm using the bad eraser. So here we are. Okay, so done erasing. Now, for the second part of my lesson, I want to give you some visual notation. And what is that visual notation? Well, I want to demonstrate the strength of an electric field. But how do I do that? Visually. How do I visually demonstrate the strength of an electric field. So let me write that down. The strength or the magnitude of an electric field. How do I demonstrate visually the strength of an electric field? Any ideas? Who's got an answer? Yes, that's right. We do use density. Okay, what do I mean by density? How do you use density to represent strength? Well, let me give you a visual picture. Let's grab into my back pocket once again, and you can see I have some marker. So let's say we have some electric fields created by this alpha particle, and it's going to radiate outwards. You're used to this by now. Now, how do I denote the strength of this electric field? This charge could be 5 coulombs, 50 coulombs, 500 coulombs, for all I care, but how do I demonstrate the strength of this electric field? One way is density. D for density. What do I mean by density? Do I mean the density that comes with mass over volume? In other words, particles per unit. What is it? What are the units for density? We have mass over volume, so something like kilograms over cubic meters. Are we talking about that type of density? No, I'm talking about area density. And what do I mean by area density? I mean, if you take some sheet of paper, let's take a sheet of paper right here, right now. So if I take a sheet of paper and I hold it perpendicular to the electric field vectors that are protruding outwards, how many of those electric fields are going to cross that plane? Let me show you that, because that might be a little bit confusing when you first hear it. If I take some kind of plane and I hold it perpendicular, you can kind of grab, lots of people have pictures of their pets hanging on their doors. Grab that picture of your pet, take out that your dog, your cat, whatever, throw it out, and take just the frame. Take that frame, hold it perpendicular to the electric field vectors that are coming out, and measure, literally count how many of those vectors pierce that frame. Okay? And then you'll have the area density of the electric field. Okay? So that's one way to demonstrate or to denote visually the strength of an electric field. What's the other way? Unfortunately, I've forgotten the other way, and I can't show you that right now. No, it's okay. We do have the other way, and the other way is using magnitude, the length. So one way was density, the other way is length. What do I mean by length? Well, I can demonstrate the magnitude of my electric field by making the vectors of my electric field longer. Simple as that, right? So for example, then let me show you, just to give you a sense of what I'm talking about, let me visually show you what I mean. So when we're talking about showing the strength of an electric field, we can use length as such. So let's say I have one positive charge that's 5 coulombs, and one positive charge that's 0.5 coulombs. Right? 0.5 coulombs. Okay. Obviously, I know that the electric fields created by the left-hand side charge is going to be greater. But how do I visually show that? Well, I can just use the length of my arrows, right? I can make this one's arrows bigger than the other ones. Okay? And for the other one, I can just make its arrows super small. Teeny tiny, something like that. Okay? And just from looking at that, you can tell that the magnitude or the strength of the electric field of the positive 5 coulomb charge is going to be something like 10 times the magnitude of the electric field of the 0.5 coulomb charge. Okay, so now we talked about the strength of the electric field. Let's move on to the exit slip. Okay, and in today's exit slip, I just want to give you the rules, well, not rules, but some of the properties of electric field. Just 3 or 4 properties that might come in handy when trying to visualize these vector fields. Okay? First and foremost, let's begin with the easiest one, which is that electric field lines shouldn't cross. Okay, so this is our exit flip, by the way, so let's just go ahead and write that down. ES, Now, first and foremost, electric field lines should not cross, right? So that means the electric field vectors would go in opposite directions. So let's write that down. Electric field lines should not and will not cross. Okay? Second property you should keep in mind is that the electric field of a conductor is going to be perpendicular to the surface of the conductor. What do I mean by a conductor? A conductor is any material in which electrons can flow easily, right? So let's go ahead and write that down. The electric field of a conductor will be perpendicular to the surface of the conductor, Okay? Hopefully all of that is fine and handy dandy. Now, do you remember when I made that analogy of holding up the paper? Let me just go ahead and grab my new pens, okay? Okay, here we are. Some additional markers. Now, why did I hark back to that paper analogy? Well, first and foremost, because our third property of electric field is that the electric field line originates on what type of charge? Go ahead and comment down below what type of charge the electric field originates from. Okay? Well, it actually originates from a positive charge. Okay? Let's write that down. Originates from a positive charge. And where does it terminate? Let's grab a red for that. It terminates on a negative charge, right? Because the negative particles field lines protrude inward. Terminates on a negative charge, right? And the fourth law is kind of colloquial, right? It's basically that the electric field at any given point in space is going to be the vector sum of all the electric fields created by all the other charges. So let me give you a picture of what that means. Great, I've run out of space, so let me just come over here to the side. So let's grab some markers here. So let's say I have this kind of annulus. Hopefully you see what I've just drawn here. This kind of annulus of charges. So here's plus, 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 all of these positive charges, right? Now, let's say I put some kind of a charge right here. This charge is obviously going to be repelled from all that ring of charges, and one charge is going to repel it this way, one is going to repel it that way, one is going to repel it that way, and so on, so forth, right? So the net electric field at that point is going to be the vector sum of all of those electric fields. We have to take into account the contribution made by the electric fields of every single charge that's in the vicinity of this test charge. Okay, folks, so thank you for watching the fifth lecture of special relativity. If you have any questions, comments, or ideas, go ahead and comment them down below. Hope you learned something, and we'll see you next time.
Subscribe to Bari Science Lab to fall in love with math and science, especially programming.